Hi, Dr. Revis here with Watch Me Work It, assigning domain names to formulas and Lewis structures by AXE or ABE format. So watch me work it. When we talk about the AXE or ABE format, it's one and the same, but some like to use AXE and some like to use ABE. I tend to use ABE, okay? But it means the same as AXE. So watch me work through these. Here we go. So we have CCO4. So CCO4, the best way to do this is to know something about the Lewis structures, by the way. So when we look at these, we look at the central atom only, and the Lewis structure helps us. Now you can draw those out, see some other videos if you need help with that, but I'm going to assume you know how to draw Lewis structures. But just to kind of keep us on track, I'm going to show you the basic dot structures of these based on what's called hybridization theory and principles. So this is what the basic Lewis structures will look like for these groups as the central atoms. And what this helps to see is what the initial lone pair and bonding patterns might look like. Didn't draw that one very well. Let me just clean that up just a little bit there. Draw that a little cleaner than I have it. There we go. Let's see what we can do with that. And then, of course, fluorine has a lot of lone pairs around it. Squeeze it in here. So this is what the initial bonding pattern looks like for these. And helium, let's just draw it up to the side. It would be 1, 2, 3, 4, 5, 6, 7, 8. So that's initially. So this gives an idea of what to expect. So let's get going with these. So carbon, here we have carbon. Carbon has the potential to bond 4 times initially. So we know when it bonds, we're going to have no lone pairs. So the A means carbon, central atom. B means how many groups are bonded, 4. And E would mean how many lone pair. We don't have any since all the valence electrons are used up for bonding. So this will be an ABE. Basically, carbon tet looks like this. I'm going to leave the electrons off the chlorines for now because they don't matter in terms of assigning ABE. The exterior lone pairs, or at least lone pairs on the exterior groups or peripheral groups, don't matter. Okay, so let's do now sulfur. So sulfur, S is a central atom. We have 4 bonded groups. We see them 4 bonded groups. This will be X by the X notation. And now how many lone pairs do we have? Well, if we go to sulfur, we expect to see lone pairs because it's in group 16, but how many? Well, we have 4 chlorines. 2 of them were used up with the unpaired electrons, the single dots. And so we had to split 1 more lone pair for the other 4, and that left us with 1 lone pair. So we have 1 lone pair. If you want to learn more about how to do that, see my other videos. So this would be an AB4E. They both have AB4, but this has E, so the geometries would be different. Let's do XEO. XE, that means you have A. You simply write A. You don't care how many letters associated with it. A is a central atom. And if we look at xenon here, we see it's going to have 8 electrons. And since we have oxygen, so that's going to be B4, by the way. Let me write that. So we have another B4 here. So we have an AB4 here, AB4 with an E here. We have an AB4 here. And now we have to determine the number of electrons. Well, as it turns out, oxygen requires 2 electrons for every bond it would like to form with this Lewis geometry. So they're all used up, so there are no lone pairs because we use up 2 times 4 here, 8. And xenon only has 8, so that. So we have here, so this would have the same, by the way, CCO4 would have the same geometry as XeO4. And just for hybridization, this is called sp3. In case you see that, this would be sp3 as well. This would be sp3. And since we have one more thing, we have to count for it, be D. Okay. Now, so let's see here for ammonia, NH3, we have the A for the N, and we have B3 for the H's. However, we note that this is in group 15, 5A, 5 valence electrons, 5 valence dots around. If we do this properly by hybridization, we'll have 1 lone pair. And so we're going to have the E here, and that's going to be a sp3 see, yeah, count here 4, yeah, sp3 here as well. The way you do this is simply count this plus that gives you the must add it to the value here. Okay, did I get 3? Yes, I did. All right, so here we are, B, F, the A for that, and we have 3 groups, B3. Now we just have to determine whether or not we have, do we have any lone pairs? No lone pairs. Boron rarely has lone pairs. It just does. Its location in the periodic table doesn't afford it. So this is going to be an sp2 because we have 3 groups around it, 2 in the P, 1 in the S. That adds up. Back here we had 4 groups, 3 here and 1 here. Okay, so let's do sulfur next. Sulfur here, if we look at sulfur, oxygen needs 2 opportunity bonds, so that's actually 2 times 3. We would use up all 60 electrons at bonding. But so this is going to be an AB3, no lone pairs. So since an AB3, this is going to also be an sp2 as well, but there are no lone pairs. When you assign the hybridization, by the way, you don't look at the A. It's just sitting there telling you it exists as a central atom. Let's do carbon dioxide. Carbon dioxide, carbon's right here. Since it uses 4 electrons for bonding, it has non-available for lone pair. So this is going to be an A for carbon, and this is going to be a B2, no lone pairs, and that's going to be just an SP because we only have 2 to accommodate here. For more on how to assign hybridization, see my other videos. Next we have neon dibromide. So neon with 2 bromines around it, so that means we have an A for neon, and it's bonded twice. And now we just need to determine how many lone pairs are here. For neon, let's go down here to neon, and it looks like helium, but I'm just going to draw neon here so you can see me do it. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to take away 2 of these for bonding. I'm left with 1, 2, 3 lone pairs, so that's going to be an E3, and I have 5 spaces to fill up. That's sp3. That fills up 4, and D makes it sp3d. All right, so this is how you assign the domain names, and by coincidence, this is how we do the hybridization.